California's ecosystems give us stunning landscapes, habitat for globally important plant and animal species, water for drinking and agriculture, and storehouses of carbon to reduce climate change. Today I will present the results of recently published research on the changes of ecosystem carbon across the state of California. And this has been a team effort with John Battles of UC Berkeley, Brandon Collins of the USDA Forest Service, Tim Robards, and David Spa. And we gratefully acknowledge funding from the California Air Resources Board and also contributions from ARB staff, including Klaus Scott, Richard Bode, Annie, who just spoke, and Webster, and other colleagues. So I will present the research in these three sections, starting off with the research question. The Intergovernmental Panel on Climate Change has detailed the global carbon budget, and we see here, can you see yes you can, good. And you see here that our power plants, cars, and deforestation pump 9 billion tons of carbon into the atmosphere a year, that oceans, vegetation, and soil naturally absorb 5 billion of those tons. Consequently, 4 billion tons goes into the atmosphere and accumulates there, and it is this fundamental imbalance that causes climate change. Human activities are causing climate change. Within this, we see that terrestrial ecosystems emit 1 billion tons globally and absorb 2.5 billion tons globally. So the carbon balance of terrestrial ecosystems is a net storage. So globally, ecosystems are serving to reduce climate change. Up until now, however, we have not known the carbon balance of California ecosystems. And so our research question is, or was, are California ecosystems emitting carbon and exacerbating climate change, or are they storing carbon and reducing climate change? Answering this question is important for one of the fundamental reasons we're all here, the California Global Warming Solutions Act, and for providing the data to the annual inventories that Anthony just described. Answering this question is also important for the U.S. National Park Service. We manage forests with the highest carbon densities in the world. Coast redwoods, 2,900 tons per hectare, 5 to 10 times the amount of carbon per square on the ground as tropical rainforest. Redwood National Park and Muir Woods National Park, a national monument. And also forests with the second highest carbon densities in the world, the giant sequoias in Yosemite, Sequoia and Kings Canyon National Parks. Our methods needed to follow both scientific and operational requirements. We needed to look at all the wildland ecosystems statewide, in a spatial manner, in a spatially explicit manner, using methods that were based on field measurements, not modeling, repeatable over time, compliant with IPCC guidelines, and with a quantification of uncertainties. As Annie portrayed, a lot of variables go into these calculations, and so you cannot scientifically give just one single number. To be valid, you need to characterize the range around the central value. In response, we developed an approach. Basically, these 7 components. We selected Landsat 30-meter resolution data that's been processed by the U.S. government land fire program. We took that data and we defined 1,083 distinctive biomass classes across the state. We used USDA Forest Service forest inventory and analysis data to estimate the biomass density, the tons per hectare in forests. And for other types of ecosystems, we used NASA MODIS data to do that. We then repeated this method for 2 different years, 2001 and 2010. And then we calculated the change in stock over that 9-year period. To quantify uncertainties, we used Monte Carlo analysis, and then we validated our results against field data that came from an independent research efforts. So I'll provide some details now on the methods. IPCC divides land into 6 categories. We look at the top 4 categories there. So everything except for urban and agriculture. So our inventory covers 83% of the state. You'll see that IPCC combines forest, shrublands, anything with trees into the same category, forest land. So in parallel, we use the National Vegetation Classification System, which discriminates between trees and shrubs. And then using land fire vegetation type, height, and fractional cover, we found the 1,083 unique combinations of those 3 variables. And those are the basic unit of the analysis, the biomass class. We used the field data to develop equations of biomass as a function of vegetation type, height, and fractional cover, canopy cover. And this is an example for the wetter mixed conifer, montane mixed conifer. For the non-tree ecosystems, we use NASA MODIS data, remote sensing, and you see here the annual net primary productivity, the average for the 9-year period, and it's greater in along the coast and decreases. And here we see that even with low vegetation, the desert and grassland ecosystems of California still have carbon. Okay, so for each of the biomass classes, we conducted a calculation, fairly straightforward, 3 main variables. The first is the surface area. The second is the biomass per unit area, the tons per hectare. And the third was the fraction of the biomass that was carbon. And okay, so these are the exact equations that we used, and we calculated the central value, and then we repeated the calculation 100 times using the different sources of air, the remote sensing air, the measurement error of people going out and measuring trees, the statistical error of the equations that we developed. And so essentially, we ran our analysis 100 times. And we did it separately for the stock, this top equation, and for the stock change. Great. Our results in 2001, 920 million tons in wildlands, plus or minus 20%. 9 years later, 850 million tons, plus or minus 20%. And for the 9-year period, we found carbon increasing on about 1/7 of the area. an increase of 18 million tons. But we also found losses on 1/5 of the area, or a decrease of 88 million tons. And so the net balance here was negative 69 million tons, plus or minus 20%. And here is the result of the Monte Carlo, and you saw the plus or minuses about 20%. And this is for the 9-year change, and so the negative 69 is here in the middle, and here's the uncertainty in the red bar. Going back to the map, which is kind of illustrates the most important result of this, you see these brown areas. Okay, the scale on this, the darkest greens are an increase of 100 tons per hectare, and the darkest browns are a decrease of 100 tons per hectare. And we see a lot of brown areas here in the South Coast Chaparral, also along the Sierra Nevada, and then also in the North Coast. Those are fires. Those are wildfires. So we analyzed that in more detail. We compared areas that burned with areas that didn't burn. And this graph shows in green the surface area of those two parts of the state, and in brown the emissions. And we see that a very small fraction of the area burned, 6%. But that 6% produced 2/3 of the state's emissions during that time. So clearly wildfire is the most important factor in the carbon stock change in ecosystems during the 9-year period. For example, in Yosemite National Park, here is a part of the Pig Meadow fire area. It burned in 2009. This Landsat real color image is a year later. And here's the carbon change, the Big Meadow fire. Remote sensing also easily picked up timber harvesting. This is private land west of Yosemite. And here's the carbon change in those timber harvest areas. Very clear. Okay, we validated our results against independent field data. And just briefly, you see outlined here in orange the comparison. Ours is on the bottom. The field research in the Sierra Nevada is on the top. You see we're very close for these two sites. And then we also compared our results to other remote sensing results of carbon stock. Nobody has used this approach to look at stock change over time. We've only done one-time research efforts looking at stock in a single year, and we see our estimates are within the error bounds of those. You also see some NRs here. Not all research quantifies the uncertainty. Okay. One detail about the carbon stock change, about 2/3 was in tree-dominated ecosystems, and 1/3 was in shrub-dominated ecosystems, mainly chaparral in Southern California. And more details on the carbon stock change, I just wanted to point out here, these are transitions among forests and the other natural ecosystems, or trees and the other vegetation orders. And I've outlined in orange here, forest going to agriculture and urban. And you see that it's 2 million tons of carbon, which is a lot, but it's actually a relatively small fraction of the total. So it is not urbanization that is the major factor. Again, we're looking at wildfires, which I'll come to again in a minute. But here's a sensitivity analysis of the different sources of uncertainty. And I've outlined in orange here that the remote sensing air from land fire was the factor that accounted for most of the uncertainty. And so that points the way to the future development here. The more accurate we can get the remote sensing, the more accurate we can get the inventory. So this pulse of carbon that we saw in 9 years is occurring after a long history of wildfire in the western United States. Wildfire is a natural and necessary part of forest ecosystems here. But of course, too much wildfire damages ecosystems and can kill people. This graph is from Jennifer Marlin's research, and the bottom line is an index of drought going back to 500 AD, and you see that it's gone up and down, and it's gone up in the last 150 years. The top lines show the biomass burning. There's two lines, a black line and a red line. The red line shows an estimate of what actually burned based on recent field measurements, but in the past, fire scars across the western United States. That's the red line. The black line is the burning you would expect given the climate factors here and the fuel factors. So we see here that in the 20th century, the fire suppression that has been the official U.S. government and state government policy was very effective. It reduced burned area substantially. At the same time, climate change has been increasing temperature, changing precipitation, increasing evapotranspiration, increasing drought. So this black line has gone up. That is the potential fire. And the difference between the black line and the red line is where we are now, and that is a situation where the potential for wildfire is great because of climate change. And Tony Westerling, who's speaking in another session, has modeled under climate change high emissions. These three maps show high emissions up to 3 times burned areas in some parts of California under the high emissions scenario. So in summary, let me encapsulate the connections between wildfire, carbon, and climate change. Fire suppression has increased fuel and the density of small trees in a century of that. We have unnatural densities of small trees and unnatural amounts of fuel. The U.S. government and the state changed their policies in the 80s, in the 70s and 80s, and now we use fire to try to bring back ecologically appropriate fire regimes to forests and other ecosystems. At the same time as that policy change, climate change has been increasing wildfire. So what we're seeing is through fire management, short-term emissions, but in the long term, if fire management is successful in reducing the density of small trees and encouraging the growth and maturation of larger densities of large, older trees, then in the long term, we'll be able to store more carbon and eventually reverse the balance. The national parks, the 26 U.S. national parks in California, besides all the other ecosystem services, provide an important ecosystem service in carbon storage, as I mentioned, with the redwoods and the sequoias. This is an example of one of the benefits of protected areas. And we see the 26 national parks have 42 million, a stock of 42 million tons of carbon, looks like plus or minus 30%. That's equivalent to 1 year of emissions from over 7 million Americans, or the population of those 6 cities. That's a lot on one hand, 7 million Americans, but it's not a lot on the other hand because it's only 1 year of emissions. You could burn off all of the carbon in the 26 national parks in California. So this points to the need for us to reduce our greenhouse gas emissions from our cars, power plants. And Annie mentioned future developments. We're working to update this to 2014 to examine improved methods for quantifying growth and examining in more detail the issues of wildfire. Thank you very much.